So, we're looking at graphing trigonometric functions, and the shape of a trigonometric function will be evidence that trigonometric functions are everywhere. There is nowhere in the world that you can go to escape trigonometry. Even right now, your body is being bombarded with billions of sine and cosine waves. So we want to know exactly what these things look like. So if you turn in your books to page 230, there's a table of all the answers for all the special angles. Usually when I teach Math 12, I make my students memorize this whole table on page 230 as a quiz. So usually this quiz is just filling out this whole table. When we were playing the special angle game yesterday, basically that's what we were doing. We're just finding the answers for this table. So if you're able to play that game, that means you probably know most of these. So just take a look at the sine list. And looking at those numbers, what's the largest number that you see underneath sine? What's the maximum? 1. What's the maximum under the cosine list of numbers? Right. And what's the minimum value of cosine and sine? -1. So sine starts at 0. It goes up to 1, goes back down to 0, goes down to -1, and back up again. Cosine starts at 1, goes down to 0, goes down to -1, up to 0, and then back up again. As theta changes from 0 to 2 pi, how do the tables of sine and cosine differ? They start differently. Do you notice any similar patterns between those two tables for sine and cosine? There's a phase shift. They're exactly the same. They have the same points, just a different start. You can see the numbers are the same. If you look at, take a look from starting from 1 with cosine, and then where 1 is with sine, and then check the numbers after that, if you follow along, they have exactly the same points. So basically what we can do is we can take these special angles and we can turn them into a graph. So we're going to graph the angle on the x-axis and the height on the y-axis, or the value of the ratio. So when the angle is 0, sine is 0. When the angle is 90 degrees, or pi over 2, sine is 1. When the angle is pi, sine is 0 again. When the angle is 3 pi over 2, sine is -1. And when the angle is 2 pi, sine goes back to 0. And I'll just connect those dots with a nice shape that looks like a cave, because it's concave down on the top half, and then a shape that looks like a bowl, which is concave up on the bottom half. And this is what I would call your basic sine graph. So your basic sine graph is this shape right here. It starts at 0, 0, goes up, down, and back up again. And now if you wanted to make the whole sine wave, you just take that and you copy paste it. So you don't have to draw on this part because we're going to actually write on the right. But basically I would take this part here and I could copy it over here. And I can copy it on the other side as well. Copy, paste. And the wave just keeps going in all directions. So we'll copy paste it very neatly on the left side, exactly the way that it is on that right side. So the right side there is all that you need to be able to form the whole wave. We go over to, down to, over to, up to, back to, up to, back to, down to. And it looks like a bowl concave up, and it looks like a cave, concave down. So some of the important features are the maximum. The maximum happens when x is equal to pi over 2. The minimum happens when x is 3 pi over 2. And the zeros are at 0, pi, and 2 pi. And you could add 2 pi to each of these answers. So there's another minimum at negative pi over 2. There's another maximum at negative 3 pi over 2. And there's more zeros at negative pi, negative 2 pi. Okay, so this repeats every 360 degrees, or every 2 pi. And this is the shape of light waves. So everything that we see comes to our eyes in the shape of a sine wave. It's also the shape of sound waves. Everything that we hear comes to our ears as a wave. And it's also the shape of your de Broglie wavelength. You also have a wavelength associated with you, but that you need a very modern physics for. But yes, you yourself are a wave. Okay, so after our foray into quantum physics and the physics of Santa, we will draw the graph of sine and cosine. So from your table on page 230, where does the graph of cosine start? When x is 0, what is y? It starts at 1. Okay, so this is the difference between sine and cosine. The shape is the same, the starting place is different. So cosine goes 1, 0, negative 1, 0, 1. From 90 degrees to 180 to 270 to 360. And this shape here is the basic cosine. If you take this shape and copy paste it, then you'll get the whole cosine graph. So when I'm modeling sound or light, it doesn't matter if I use sine or cosine. The part in the middle looks like a bowl. It's concave up. And the part on the side looks like a cave. It's concave down. And then if I copy paste that shape, then I fill up the rest of the graph with my cosine. So the important things are that the maximum this time is at 0 and 2 pi. The minimum's right in the middle at 180 degrees, or pi. And the zeros are at 90 and 270, or pi over 2, and 3 pi over 2. I can just take that basic shape and copy paste it forever, and I'll get the rest of the graph of cosine. So can you tell how much I have to shift cosine to get sine? Just 2 of those little squares. From here to here. Pi over 2, or a 90-degree phase shift. So if I shift the graph over 90 degrees, then sine turns into cosine turns into sine. Now the graph of tangent is sine divided by cosine. So I can just take the y value of the sine graph divided by the y value of the cosine. So here y is 0, y is 1. 0 divided by 1 is 0. On sine, y is 1, cos is 0. 1 divided by 0 is undefined. So there's asymptotes. Whenever cosine is 0, there's an asymptote. So the asymptotes will happen at the same places where cosine is 0. Pi over 2, 3 pi over 2. Whenever cosine is 0, tangent will have an asymptote. And when sine is 0, when the top is 0, then tan will also be 0. So tangent zeros happen when the sine function is 0 at 0, pi, 2 pi. And tangent has this really weird, almost like a cubic function sort of shape. So the basic tangent graph is this one right here. And you can see that tangent repeats more often. I only need to take 180 degrees of tangent, and then I can copy paste those. So let's see, the points are, the asymptotes happen at 3 pi over 2 and pi over 2, or 90 and 270, and the zeros are at pi, 2 pi, negative pi, negative 2 pi. Oh, the beauty of this. It's so beautiful. It connects circles and triangles, waves, everything that we experience in life. I just want to go back up to the top just for a moment to connect this back to the unit circle. So you remember what sine theta is, right, in terms of like x, y, and r? Y over r. And if r is 1, so if the radius is 1, then this is just y. Right? Sine is the y coordinate. So if we're going around in standard position, we start here. The y coordinate is 0. And then as we go up, the y coordinate goes from 0 up to 1. So that's this part of the graph right here. This part of the graph represents quadrant 1. The sine is just the y coordinate. So I'm going from y equals 0 all the way up to y equals 1. Can you see quadrant 2 on your graph? It's the next section. The next section is quadrant 2, when it's going from 1 back down to 0. And then the y coordinate gets negative and goes from 0 to negative 1. There's quadrant 3. So you can see that sine is negative once you get past 180. And then quadrant 4 is from negative 1 back up to 0. Do you see the connection? Okay, so it's just determining the y coordinate, how high my finger is as I go around the unit circle. And the cosine graph is the x-coordinate. So the x-coordinate starts at 1, and then goes down to 0, to negative 1, and then back to 0. All the way, and once you get all the way around the circle one time, the x-coordinate's back at 1. So the cosine graph is just the x-coordinate as you go around this unit circle. So that's basically, and that's why cosine is positive in quadrant 1 and in quadrant 4. Cosine is negative in quadrant 2 and quadrant 3. Oh, it's so beautiful. Cosine and sine are periodic functions, so that means that they repeat themselves every so often. And the length of the shortest part that repeats is called the period. And the period can be the distance from a maximum to a maximum, which is the same as the distance from a minimum to a minimum. That's the easiest way to find the period. If you change the period of light, then you get different colors. If you change the period of sound, then you get different notes, high notes or low notes. So this affects color for light and affects pitch for sound. So if we want to find the period of a wave like this, we can just find out how many boxes does it take to go from maximum to maximum or minimum to minimum. So I think the minimum to minimum might be the easiest here. So we can find out what is the distance from here to here. And that's called the period. It looks a little bit less than 2 pi. So I'll just count how many boxes I have. 1, 2, 3, 4, 5, 6. Each of the boxes is pi over 6. So that means I'm going from pi over 6 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, is my pi in the wrong spot? This is just one box shy of 2 pi. So 11 pi over 6. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, is it over 7? Did I count that wrong? Let me try again. 1, 2, 3, 4, 5, 6, 7. Yes! This is 7 pi's out of 7. 8, 9, 10, 11, 12, 13, 14. I counted it incorrectly. So I have 1 pi out of 7 all the way up to 13 pi's out of 7. So that total period is 12 boxes, and each box is 1/7. Boxes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12, and each one is pi out of 7. So it takes me 7 boxes to get to pi. Now we can graph this on the graphing calculators. So if you take out your calculator, let's put in sine and cosine from negative 2 pi to 2 pi and just see what they look like when we put them on top of each other. There's a really nice tool that you can use to graph sine and cosine functions, which is Zoom Trig. So I'll walk through this with you. So you graph sine x and cosine x, and then you go to your zoom menu and choose number 7. And it chooses a really nice window for your trig function. You go to your zoom menu and choose zoom number 7. So make sure you're in radian mode. And then choose zoom number 7. And we can graph that right on the paper. So cosine starts at 1. And sine starts at 0, 0. And we can calculate the intersection points. Calculate the intersection. Enter, enter, enter. So it crosses at 0.78 and 0.707. So the red one is the sine graph. They both have the same shape, but a different start. What's the period of the function? What's the distance from a maximum to a maximum? How long does it take for sine to repeat itself? 2 pi. That's why we're always adding 2 pi in. And cosine's the same. Cosine repeats after 2 pi. The coordinates of the point of intersection, let me check those numbers. I think that would be pi over, nope, pi over 4. Oh, there's the x-coordinate. Anybody know how to get 0.707? One divided by what? Root 2. It's magic. Okay, because at 45 degrees, the sine and the cosine are the same. Where else is sine and cosine the same? Another quadrant?
No.
Root 2, negative 1, negative 1. So that would be 1, 2, 3, 4, 5 pi over 4. So at 5 pi over 4, they're both negative. And that is this point right here. 5 pi over 4 and negative 1 over root 2. And then we could also add or subtract 2 pi to those points. So this point would be the point negative 1, 2, 3 pi over 4 and negative 1 over root 2. And this one is just going backwards around the circle. 1, 2, 3, 4, 5, 6, 7. Negative 7 pi over 4 and positive 1 over root 2. Okay, so these waves are really closely connected to the unit circle that we just learned about. And, oh, sorry. And now we're going to connect it all back to unit 1. We're going to take sine and cosine functions and transform them because we want to be able to graph any wave, any light wave, any sound wave with any frequency or period, and any amplitude, any phase shift. So the A at the beginning is just like the A in A f of x minus c plus d. The A affects the amplitude. That stretches it or reflects it. Do you remember the C moves it left or right? And the D moves it up or down. So I'm missing a letter here in my transformations. The B, I'm missing the horizontal compression because it's quite complicated. We'll do that next time.
Oh, I thought you were going to say, don't do that first. Okay, so when you see something written as like cosine x plus 1,
This means that the plus 1 is after the cosine. So can you guess in your head what that's going to look like before we graph it?
Yes.
This is changing the d value. It moves it up or down. This could be a logo. So we're going from negative 2 pi to 2 pi. And the y value is from negative 4 to 4. So the basic cosine has this shape. If we move it up 1, it's just going to hit the graph on the x-axis. If we move it down 1, it's going to start on the x-axis and bounce off kind of like a ball. Okay, so that's called vertical displacement. Vertical displacement changes the d value. Amplitude changes the a value. For a light wave, amplitude affects the brightness. And for a sound wave, amplitude affects the loudness. So more amplitude means more sound. And amplitude is just the height of the wave. So just taking a look from the middle line, amplitude tells you how far above you are from the line or how far below you are from the middle. And amplitude is always positive. And it's also half of the distance from the minimum value to the maximum value. And for a normal sine or cosine, the amplitude is 1. Because we go from negative 1 to positive 1. So the first example is y equals 3 sine x. Do you know what the amplitude of that wave is? The amplitude is just the number in front, just your a value. Okay? And what that means is that the normal graph of sine has been stretched 3 times. So it's 3 times higher than it usually is. And the zeros don't change, it just becomes a lot higher. So normally, sine looks like this. And usually it goes from 1 to negative 1. But if I make it 3 times higher, it's going to look like this. So there's y equals 3 sine x compared to the normal sine x. And let's just confirm that. Three sine x. I'm going to change my window so that it matches my picture from negative 3 to 3. Whee! That's a better roller coaster than the sine function. And there's another application of sines. So this is going from 2 pi to 2 pi and from negative 3 to 3. So looking at the second graph, do you know what the amplitude of this graph is? It's a half. It's just the number that's in front of the cosine. And amplitude will always be positive. So if there's a negative number, the amplitude is positive. This will be a question on your test. I'll just give you a function and ask you what's the amplitude. You just look for whatever number is the A value. So this one is now a compression and a reflection. Do you know which axis it's reflected in? X. Nice. Can you draw it without using your calculator?
Yeah, sure.
Yeah, let's draw the normal one in red. So my normal cos starts on the top and goes down. If I reflect it, now it's going to start halfway. And it's only going to go up to a maximum of 1/2 instead of a maximum of 1. And because it's getting flipped, it starts on the bottom and then starts to go up. So for practice today, take a look at page 250, numbers 4 to 17. These are all multiple choice. Yes, we're starting review, but no, that doesn't mean that there's the test coming soon. The next section we're going to be doing as a project, so it'll be a while before the test. I will see you tomorrow.